When you rub a balloon onto your hair, the hair tends to stick to the balloon. Why do you think this happens? Property that protons and electrons possess, because of which they can attract and repel other protons and electrons. We call this the electric force. And of course, today we have discovered so many other particles that also possess this thing called as charge. In this video, we will look at what the symbol and the unit for electric charge is. So the symbol for the electric charge is Q. And we measure it in a unit called coulombs. Coulombs, denoted by a capital C. So just like how we measure mass in kilograms and we measure height in, say, meters, we measure charge in coulombs. And the word Coulomb is named after the scientist, the French scientist Charles Coulomb, who did a lot of work in investigating the force between these charged particles.
There's a law in physics that has stood the test of time. Laws come and go. Sometimes we discover new things, we have to scrap them, amend them, adjust them, tweak them, throw them away. But there's one law that has been around for a long time, and no one has ever tried to damage this law or discovered any experiment that has shown it to be wrong, and it's called the law of conservation of charge. And this is electric charge is what we're talking about in this particular example. So what does this mean? Well, imagine you had a box, and inside of this box I'm going to put some charges. So let's say we have a particle here and its charge is positive 2 coulombs, and then we have another charge flying around in here and it has a charge of negative 3 coulombs, and we have another charge over here that's got, I don't know, positive 5 coulombs. These are flying around. What the law of conservation of charge says is if this box is closed up in the sense that no charge can enter or exit. So I'm not going to let any charge come in, and I'm not going to let any charge go out. If that's the case, the total charge inside of this region of space has to be constant when you add it all up. So if you want a mathematical statement, I like math. The mathematical statement is if you add up, this sigma is the fancy letter for adding up, all the charges in a given region, as long as, here's the asterisk, as long as no charges are incoming or outgoing, then the total amount of charge in that region of space has to be a constant. This math looks complicated. It's actually easy. All I'm saying is if you add up all this charge, you ever open up this box, you're always going to find 4 coulombs in there. Now this sounds possibly obvious. You might be like, duh. If you don't let any of these charges go in or out, of course you're going to only find 4 coulombs in there because you've just got these 3 charges. But not necessarily. Physicists know if you collide 2 particles, these things don't have to maintain their identity. I might end up with 8 particles in here at some later point in time. And if I add up all their charges, I'll still get 4. That's the key idea here. That's why this is not just a frivolous, sort of meaningless, trivial statement. This is actually saying something useful. Because if these were protons, they're not, because this is a positive 2 coulomb and the proton has a very different charge. But for the sake of argument, say this was a proton, runs into some other particle, an electron, really fast. If there's enough energy, you might not even end up with a proton and an electron. You might end up with muons or top quarks, or if this is another proton, you end up with Higgs particles or whatever. And so at some later point in time, here's why this law is important and not trivial. Because if this really is closed up, and the only stuff going on in there is due to these and whatever descendants particles they create, at some later point in time, I may end up with, like, say this one, it doesn't even have to have the same charge. Maybe this one's positive 1 coulomb, and I end up with a charge over here that has negative 7 coulombs. If these were fundamental particles, they would have charges much smaller than this, but to get the idea across, big numbers are better. And let's say this is negative 4 coulombs, and then you end up with some other particle you didn't even have there. None of these particles were there before. and some charge q. Now we end up with these 4 different particles. I don't know, these combined, there was some weird reaction and they created these particles. What is the charge of this q? This is a question we can answer now, and it's not even that hard. We know the charge of all the others. We know if you add up all of these, you've got to add up to the same amount of charge you had previously, because the law of conservation of charge says if you don't let any charge in or out, the total charge in here has to stay the same. So let's just do it. What do? We add them all up. So I get negative 10 coulombs plus, oh, you know, these q's look like 9s. Sorry about that. This is law of conservation of charge. I might add a little tail. This isn't the law of conservation of 9s. So this is a little q. This is a little q, not a 9. And so plus q equals 4. Now we know that charge has to have a charge of 14 coulombs in order to satisfy this equation. But you don't even really need a box. I mean, no one really does physics in a cardboard box. So let's say you were doing an experiment and there was some particle x, an x particle, and it had a certain amount of charge. It had, say, positive 3 coulombs. That would be enormous for a particle. But for the sake of argument, say it has positive 3 coulombs. Well, it decays. Sometimes particles decay. They literally disappear, turn into other particles. Let's say it turns into a Y particle and a Z particle. Just give them random names. And you discover that this Y particle had a charge of positive 2 coulombs. And this Z particle had a charge of negative 1 coulomb. Well, is this possible? No, this is not possible. If you discover this, something went wrong. So because this side over here, you started off with positive 3 coulombs. Over here, you've got to end up, according to the law of conservation of charge, with positive 3 coulombs, but positive 2 coulombs minus 1 coulomb, that's only 1 coulomb. You're missing 2 coulombs over here. Where'd the other 2 coulombs go? Well, there had to be some sort of mystery particle over here that you missed. Something happened. Either your detector messed up or it just didn't detect a particle that had another amount of charge. How much charge should it have? This whole side's got to add up to 3. So if you started off with 3, over here, these two together, Y and Z, are only 1 coulomb. That means the remainder, the 2 coulombs, the missing 2 coulombs has to be here. So you must have had some particle or some missed charge that has positive 2 coulombs. Is that another Y particle? Maybe. That's why physics is fun. Maybe it is now. Maybe you missed another one. Let me ask you this. So let's say we get rid of all these charges. Here's one that freaks people out sometimes. Take this. Let's say this had no charge. No charge. It was uncharged. You had some particle with 0 coulombs. Is it possible to end up with particles that have charge? Yeah, it can happen.
And to give you a sense of how big a coulomb is, turns out that the charge on an electron or a proton is a very, very small fraction of a coulomb. So if you were to look at the charge on an electron, which we usually represent as E, it turns out to be so small. Let's see, we write it as 0.00, and there are so many zeros, I can't write them all. 0, 1, 6, and some other numbers, coulombs. And the number of zeros over here are 18. There are 18 zeros in between. Just goes to show you how small the charge on the electron or the proton is. So the electron has this much charge, but it's negative. Proton also has the same value of the charge, but it's positive. So they have the same values, but one has positive charge and the other one has negative charge. And of course, since it is so small, we often like to represent this in the scientific notation. So we will shift this decimal all the way till here. And we'll write it as 1.6 times 10 to the power. Now let's see how many times we have shifted it. To shift it from here to here, we shift 18 times, and then 1 extra shift, 19 shifts to the right. And so we'll write this as negative 19 over here. So many coulombs is the charge on an electron or a proton. Now, since Coulomb is a brand new unit for us, it would be nice if we could get some sense for how big it is. Just like how we have some sense for what a kilogram is, or how big 1 meter is, it would be great to have some sense for what or how big a Coulomb would be. So to do that, here's how I like to think about it. Now that we know that the charge on an electron or a proton is such a small number, for electrons it would be negative, for protons it would be positive, we could ask ourselves how many, say, electrons would make up a total of 1 Coulomb charge. You get it? So it's going to be a huge number because charge on each electron is so tiny. We need a lot of electrons to make up 1 Coulomb. But exactly how much is the question. So let's think about this. Let's go down a little bit. And so here's the question. How many electrons together make up a negative 1 Coulomb worth of charge? So great idea to pause the video first and see if you can try to do this yourself. Using this information, try to figure this out yourself first. All right, let's do this. So to do this, we know 1 electron. So let's write that down. We know 1 electron is worth a charge of 1.6 times 10 to the minus 19 coulombs. And since it's an electron we're dealing with, it'll be negative. But I want 1 Coulomb worth of charge, not this. So to make this right-hand side 1 Coulomb, I will divide the right-hand side. Let's divide the right-hand side by 1.6 times 10 to the minus 19. So that this will cancel and become negative 1 Coulomb. So I'll have to divide the left-hand side as well by 1.6 times 10 to the power minus 19. So on the left-hand side, we have 1 divided by 1.6. Let's bring in my calculator and see what that gives me. So it'll be 1 divided by 1.6. That will be 0.625. So that will be, on the left-hand side, 0.625. That's 1 divided by 1.6. And this will become 10 times 10 to the power plus 19. Plus 19. And that, so many electrons, is equivalent to now a charge of negative 1 Coulomb. So to get 1 Coulomb worth of charge, we need so many electrons. So many. And of course, we can also write it in proper notation. It will be 6.25 times 10 to the power 18 electrons. We shifted 1 0 by borrowing 110. So anyways, these many electrons, such a huge number, 10 to the 18 electrons, these many electrons together make up a charge of negative 1 Coulomb. And so, whenever I ask myself, how big is a Coulomb, I like to think of it as 1 Coulomb is equivalent to so many electrons. You take so many electrons together, that itself represents what a Coulomb is. That's how I like to think about what 1 Coulomb is. So to summarize, what we learned in this video is the unit for electric charge is coulombs. We saw what the charge on the electrons and the protons are. And we also saw that 1 Coulomb, how big a Coulomb is. It's equivalent to so many electrons or so many protons, because the protons and electrons have the same value of charge, but one is positive, the other one is negative.
Today, we're ready to start 802. We're going to start by talking about charge. What is charge? All matter is made up of charged particles, electrons and protons. And the electrons have negative charge, the protons have positive charge, so matter in this room under normal circumstances is neutral. It has equal numbers of pluses and minuses. We'll do more quantitative things later, but what are the units of charge? Well, the unit of charge is called the Coulomb. And you can tell that the Coulomb is a very big amount of charge because it takes 1.6 times 10 to the 19 electrons to make 1 Coulomb of charge. So we will often talk about the charge of a single electron, and that we will call minus E. So this 1.6 times 10 to the 19 is completely arbitrary. That's just the
fact of the way human beings set up their units. Although actually, I will tell you, it's actually not totally arbitrary. We'll see many, many weeks later that there was some good sense behind this seemingly bizarre choice, but that's for much later. The things I want to focus on today are not quantitative, but qualitative. Two very basic features of charge is that it's quantized and it's conserved, and I want to talk about each of those. So what does it mean that it's quantized? Well, it means that the charge of any object in the world is an integer. It's either minus e or plus e or minus 27e or plus 53e. And that's because it's made up of electrons and protons, and the charge of the proton is exactly the opposite as the charge of the electron. So one of them is minus e, that's the electron. One of them is plus e, that's the charge of the proton. So that is what we mean when we say the charge is quantized. Except for the fact that I actually just lied. There are, if you get to look inside a proton, there are quarks inside with charges of either 1/3 e or minus 2/3 e. But those quarks are always bound up together inside of a proton. So long as you never actually try and take a proton apart and look at the quarks inside, what I said a second ago is true. This fact that I've just told you about charge being quantized, that's actually an experimental fact. There's no profoundly understood reason for it. We could imagine living in a world in which charge came in arbitrary fractions, even non-rational amounts. But the world we actually live in, charge is quantized in units of E. And this is something that experimental physicists regularly test. They regularly do experiments with greater and greater and greater precision, looking to really check, is the charge of the electron minus 1.00000 times the charge of the proton, or maybe it's 1.0001. That's regularly tested, and to the best of anyone's ability to do any experiment, it has always turned out to be that the charge of the electron is exactly minus the charge of the proton. Now, what about charge being conserved? That's fundamental also. And we're going to be doing some experiments ourselves to see what that means. What does charge is conserved? What do those words mean? It means that I can't make charge out of nowhere. If I want to make it charge an object up, the way I do that is by separating positive and negative charges. So this is a plexiglass rod. It's right now neutral. I'm going to make it positively charged, and I do that by ripping some electrons off of it, getting them onto this fake fur. So I claim that now, after rubbing the rod like this rod is positively charged, and this fur is negatively charged. But the total charge of the two together is the same as it was before, which is 0. So the conservation of charge means that I can move charge around. I can take some negative charge off the rod and get it onto the fur, but I can't create net charge out of nothing. Okay, so how am I going to convince you that this object is now charged? Well, I'm going to do that by bringing it near the tinsel. You see the tinsel reacting to the presence of the rod. In fact, I'm going to transfer some charge from the rod onto the tinsel. And if you look at the tinsel now, you will see that the different strands of tinsel are being pushed away from each other. That's because all those strands of tinsel now are themselves charged. And the third basic fact about charge that we're going to see today is that like charges repel and opposite charges attract. So all of those bits of tinsel have the same charge, by convention called positive, and they're repelling each other. And if what I'm telling you is true, this is positive, the tinsel is positive, and the rod should repel the tinsel. And you see that as I bring the rod close and you can see that my positive rod is pushing the positive tinsel away. That tells you that the rod and the tinsel have the same charge, and this is, by convention, the charge that we call positive. Now, if charge is conserved, there has to be negative charge somewhere, and it has to be on the fur. So let's see what happens if I bring the fur close to the tinsel, and you see that the fur is attracting the tinsel. So one last thing I want to do is I want to show you what happens when I bring a charged rod right next to a neutral balloon. And let's see whether we can see the charged rod attracting the balloon. Look at that. Now, that balloon was neutral. How do I convince you it's neutral? Well, I'm going to ground the balloon just so you believe me that it's neutral. That's a neutral balloon. And I'm charging this rod positive. And I bring the rod close, and the rod is very definitely attracting the balloon. I can pull the balloon all the way over here with my positively charged rod, and yet the balloon is neutral. So how is that working? The key thing is that the balloon is a conductor. So when I bring the positive rod next to the balloon, what's happening inside the balloon is that charge is being separated within the balloon. And we get a little extra negative on this side, a little extra positive on that side, because the positive rod is sucking negative charge this way, inside the balloon. And as soon as that happens, then I have the negative side of the balloon close to the positive rod, and so the positive rod is now attracting the negative side of the balloon. So my balloon is at this moment neutral in total, but it has a negative side and a positive side, and the positive rod is attracting the negative side of the balloon, and that's what's going on here. So these are very simple demonstrations, but they show you that opposite charges attract, same charges repel, and that the way you charge an object up always involves separating charge because charge itself is conserved.
It's useful to pretend like all materials in the universe can be broken down into a category of insulator, electrical insulator, or electrical conductor. Now that's not completely true. There are semiconductors and superconductors and other exotic forms of electrical materials, but for most introductory physics classes and problems and tests, you can get pretty far assuming that it's either an insulating material electrically or a conducting material electrically. And before I talk about the differences between these, here I have two solid cylinders of either an insulating material or a conducting material. Before I talk about the differences, one similarity is that both insulators and conductors are composed of a huge number of atoms and molecules, and these atoms and molecules, whether it be insulator or conductor, are composed of a positively charged nucleus and a negatively charged swarm of electrons that surround that nucleus. Another similarity is that for both conductors and insulators, the positively charged nucleus cannot move. I mean, it can wiggle around and jiggle just from thermal vibrations, maybe a little bit in place, but it can't travel freely throughout the material. For either an insulator or a conductor, as long as it's a solid, if it was a fluid, I suppose these things could move and migrate around, but for a solid, the positively charged nucleus is fixed. They're stuck. The thing that might be able to move are the negatively charged electrons, and here's the difference. There are electrons in a conductor that can move about relatively freely. These can move around with almost no resistance. Whereas for insulators, the key difference is that these electrons cannot move around freely. These don't have the right energy levels and bands in order to make these electrons move around freely. They're also stuck. For insulators, everything's basically stuck. These electrons might be able to jump around in their own atom or get shared with a neighboring atom, but it can't jump around freely from atom to atom and travel throughout the insulator. For the conductors, the electrons can do this. That's the key difference. Now, the electrons aren't going to just do this on their own. They'd have to be compelled to start moving by hooking this up to a battery or setting up some sort of electric field or force. And if that did happen, then the electrons in a conductor could start migrating down the line. But in an insulator, the electrons are stuck, which might make you think that, well, okay, shoot, for electrical materials, all we really care about are the conductors. The insulators we just use if we don't want electrical interaction. And while that's somewhat true, it's not completely true, because if I set this insulator up to a battery, or I set up some sort of electric field or force in here, even though the electron in an insulator can't jump from atom to atom, what it can do is it can shift. This nucleus and the cloud of electrons can kind of shift a little bit. Positive maybe this way, and then the negatives over on the other end. So what you'd get is that overall, this side of the atom would be more negative, and this side of the atom would be more positive. And even though the electron doesn't move and the electrons don't move, now because this is set up where the positive is shifted from the negative, this material, if you get all of them to do this, or a lot of them, this can create an overall electrical effect where this insulator can interact with other charges nearby and exert forces on them. So even though the charges can't flow through an insulator, they can still interact electrically. Let's say I just add a negative charge here and a negative charge there and here and there, and I've added a bunch of negative charges to this insulator. What would happen? Well, we know these negatives can't move throughout an insulator. Charges can't flow through an insulator, so they're stuck, which means for an insulator, I could charge the whole thing uniformly if I wanted to, where the charges spread out throughout the whole thing. Or I can make them bunch up on one side if I wanted to, and they'd be stuck there. But the point is that they're stuck. For a conductor, what would happen? If I tried to put a negative here and a negative there, some extra negative charge on a conductor, they don't have to stay here if they don't want to. And if you put extra negatives in here, they're not going to want to, because negatives repel each other. Just like opposites attract, like charges repel. So what are they going to do? Well, this negative is going to try to get as far away from the other negative as it can. It's going to go over here. This negative is going to try to get as far away as it can. It repels it. Now, it can't jump off the conductor. That takes a lot more energy, but they can go to the very edge. And that's what charges do for conductors. If you got a solid conducting material, you put extra charge on it, it's all that charge is going to reside on the outside edge, whether you've added extra negative or positive, always on the outside edge. So you can only add charge to the outside edge for a conductor, because if it wasn't on the outside edge, it'll quickly find its way to the outside edge because all these negatives repel each other. And I said this is true for positives or negative. You might wonder, how do we add a positive? Well, the way you add a positive is by taking away a negative. So if you started off with a material that had just as many positives as negatives and you took away a negative, it's essentially like adding a positive charge in here. But again, the net positive charge, the net negative charge always resides on the outside edge of a conductor because charges try to get as far away from each other as possible. So what physical materials actually do this? What physical materials are insulators? These are things like glass is an insulator, wood is an insulator, most plastics are insulators. All of these display this kind of behavior where you can distribute charge and the charge can't flow through it. You can stick charge on it. In fact, you can stick charge on the outside edge and it would just stay there. And there's conductors. These are things like metals like gold or copper is typically used because it's kind of cheap, cheaper than gold certainly, and or any other metal, silver works very well. These are materials where charges can flow freely through them. So now that we see how conductors and insulators work, let's look at an example. Let's say you had two conducting rods. Say these are made out of metal, and one of them has a net amount of negative charge on it, which is going to reside on the outside edge, because that's what net charge does on a conductor. But this other rod, this other metal conducting rod, does not have any net charge on it. And also, you can get clever. You can do something called charge. You can charge something by induction, it's called. This means if you took a charged rod, brought it to an empty soda can, let that can sit on the table in this orientation so it could roll. If you bring the rod close, the can will start moving toward the rod. It's kind of cool. You should try it if you can. But that's not charge by induction. Charge by induction is something more. It says, all right, take this piece of metal and conduct it to ground. What's ground? Well, it could be the ground. If you took a big metal pipe, stuck it in the ground, that would count. Or any other huge supply of electrons, a place where you can gain, steal, basically take infinitely many electrons or deposit infinitely many electrons, and this ground would not care. So the frame of your car, the actual metal, is a good ground because it can supply a ton of electrons or take them. Or a metal pipe in the earth, some place you could deposit electrons and take them, and that thing won't really notice or care. Now what would happen if I bring this negative rod close to this rod that was originally had no net charge? Now, instead of just going to the other side of this, they say, hey, I could just leave. I'm going to get the heck out of here. These negatives can leave. A whole bunch of negatives will start leaving. And what happens when that happens is that your rod is no longer uncharged. It has a net amount of charge now. They won't all leave. You're not going to get left with no electrons in here. There's going to be some electrons in there. But some of the electrons will leave, which means this rod, which used to be uncharged, now has a net amount of positive charge in it. So I've charged this rod without even touching it because I let those negative electrons leave. And if I'm clever, what I can do is I can just cut this wire before I take away the thing that induced the charge. If I remove this now, move it far away, what these negatives would have done is they would have said, phew, okay, I'm glad that's over. Now I can rejoin. I'm attracted to this positive again. I'm going to rejoin my positive, and this thing would become uncharged again, but now they can't get back. They're stuck. There's no way for these to get back because you've cut the cord here, and you've permanently charged this piece of metal without even touching it. It's called charge by induction. It's a quick way to charge something up.
So, last time we learned how to charge an object up. We learned how to take an object and give it a net electric charge. Once we have charged objects to play with, what we discover is that they feel forces. If I have two objects here and they have the same charge, either both positive or both negative, they repel each other. They push each other apart. On the other hand, if I have two objects here and one of them is positively charged and one of them is negatively charged, they feel a force, and the force attracts them towards each other. So, doing this concretely on the board, if over here I have a positively charged object with a charge that I'm going to call Q1, positive as I said, so we are always going to use the letter Q for the charge of an object. And then suppose that up here I have a second object, which is also positively charged, but maybe it has a different positive charge, so I'll call its charge Q2, also positive. Then in a situation like this, I have two positively charged objects. They feel a force, and the force on these objects does not point in any random direction. This object doesn't feel a force pointing off this way or some crazy direction. The force is central. A central force is a force that points along the direction of joining the two objects. So this object feels a force in this particular direction, shown here, and we're going to call this force F12. And this object, again, feels a force not in some crazy random direction, but in this direction, and we will call this force F21. So a word about this notation. When I write F12, what do I mean? I mean the force on object 2, the second digit here tells me that this force, shown by this vector, is the force on object 2 caused by the interaction between the two objects 1 and 2. So it's the force on this charged object caused by the interaction between these two objects. These two objects are positive. They feel a force that is repulsive, and the force on this one, object 2, is this direction and is F12. Similarly, F21, that's the force on object 1 because of the interaction between 2 and 1. So it is a vector pointing in this direction. Now, in the other possible case, let's suppose that I have a positive object here with a charge Q1, positive. But this time, let's suppose that the other object, which, I don't know, I'll put it right there, it has a charge Q2, but this time, this Q2 is negative. So in this case, once again, the force is central. The forces on both these objects point along this line, joining the two of them, but this time, the forces point this way. This force, again, is the force on 2 caused by the interaction between 1 and 2. And this force, again, is the force on 1 caused by the interaction between 2 and 1. But this time, the forces point towards each other. The positive and the negative objects are attracted to one another. What we're going to see is that the electric force, shown by these white vectors, is, when written as an equation, very similar to the gravitational force between two objects. What you learned in mechanics was if I had two objects with mass m1 and m2, there was a force of gravity between them. But the central difference between electric forces and gravitational forces is that in gravity, the vectors always point out like this. Gravity always sucks. Gravitational forces can only ever be attractive. Whereas in electromagnetism, electric forces, they can be attractive like here, but they can also be repulsive like here. This possibility does not exist on the gravitational side. So if I want to write, for example, F12 as an equation, how do I do that? Well, the first important fact about F12 is how to write its direction. And the way I'm going to write its direction is I'm going to define a unit vector, which I will show right here. I'm going to define a unit vector, which I will call r hat. And r hat, and in fact, I'll call it r hat 1, 2. R hat 1, 2 is the unit vector that points. It's a unit vector pointing from 1 in the direction of 2. And F12 is in the direction r hat 1, 2. And from experiment, we learn that the electric force between two objects is proportional to both their charges. So it has a strength that is written as Q1 times Q2. And what you see from this is that right away we get the basic feature that like charges repel and opposite charges attract. We get that just from what I've written so far. The equation isn't done yet. but you already have, if Q1 times Q2 is positive, then F12 points in the direction of R12, which is this case. If Q1 times Q2 is negative, which means if they have opposite charges like here, Q1 times Q2 is negative, then F12 points in the minus R12 direction, which is what I've shown there. This F12 is pointing in the minus R hat 12 direction. We get that just from this. And then, just as in gravity, the strength of the electric force falls off like 1 over the distance between the two charges squared, where this distance r is the distance between these two objects. So the farther apart they are, the weaker the force, and the force falls off like 1 over r squared. And then the last thing is we need a fundamental constant of nature. For gravity, the fundamental constant that went here was called Newton's constant. There is a different fundamental constant of nature that goes here, which we are going to refer to as K. And this equation, which describes the force between two charged objects, is a fundamental law of nature based not on earlier principles, but based on things we have observed about how charged particles how charged objects behave. It's based on measurements and observations of nature. And it's referred to as Coulomb's law, named after a French scientist from the late 1700s, who was the first person to articulate this fundamental law of nature as we now understand it.
How did Coulomb discover that the force is proportional to both of the charges? The charged spheres he used in his experiments were conducting, and he had previously found that when you touch a metal sphere with an identical but uncharged sphere, the charge would split evenly between both spheres. As such, he had a reliable way of halving the amount of charge in a sphere. When he did this, he found that the force was halved. Multiple tries with both charged spheres showed that the force between charged spheres is directly proportional to the product of both charges, Q1 and Q2, since halving any of the charges would always halve the force. In this way, Coulomb found experimentally that the force is proportional to the value of both charges.
We are going to investigate a universal law of force between electric charges. At small distances, electric forces compete well with gravity. Turn on my charging arrangement, please. Give a charge to the balloon. Collect a like charge on my balloon. They repel. At closer approach, more. Bigger force. Now, farther away, less force. Still farther, very little force. Now give an opposite charge, and I get attraction. What is the exact relationship between force and distance? You probably know already. Coulomb's law says force varies inversely as the square of the distance between the charges. That means that at twice the distance apart, the forces are a quarter as big, and at 10 times the distance, they drop to 100th. An inverse square law applies in many cases. For example, the illumination due to a small lamp, when light spreads out in straight lines through clear air, not in fog or muddy water that absorbs the light. Here are 3 books at so much, twice the distance, 3 times the distance from a small lamp. The inverse square law is characteristic of anything that spreads out in straight lines without getting lost. I think I can illustrate that with a fable. Suppose a restaurant has the problem of buttering toast and wants to be very modern and do it with a machine. So the proprietor invents a butter gun with melted butter in here, which can be squirted out in straight line spray of butter like that. Here's the piece of toast, and lines of butter go out and hit it there, and there, and there, and there, and butter it all over. Now, instead of that, lines might go on, and you could put the toast further back at twice the distance, 2 pieces of toast wide, 2 toasts high, and altogether you would put 4 pieces of toast there to intercept the butter, and you'd be half a stick, no, quarter a stick buttering. Inverse square law. At 3 times the distance, 3 pieces of toast, 3 pieces of toast, altogether 9 pieces of toast, and you would get 1/9 of the buttering economy treatment. A century after Newton guessed at an inverse square law for universal gravitation, Couloumb guessed at a similar law for electric forces.
The 1 over 4 pi epsilon 0 term comes about due to the fact that we use SI units. Because of the way we define the Coulomb, meter, and the Newton, we put in a multiplicative factor 1 over 4 pi epsilon 0. Why don't we just call this factor by another name, say k? In fact, Coulomb's law is sometimes written like that, but the constant k is called the Coulomb factor. However, the reason why we choose to express this as 1 over 4 pi epsilon 0 is that when you go further into electromagnetism, the factor epsilon 0 turns up more often by itself without the 4 pi, and so we prefer to express the factor in terms of epsilon 0.
Let's consider 2 charges, Q1 and Q2. And we wrote down Coulomb's law, R hat 1, 2, and the force on that charge is our constant K, Q1, Q2 over R12 squared, R hat 1, 2. Now, one of the issues in applying Coulomb's law is this is an abstract expression. And we'd like to even make it a little bit, one more version of it. Let's write the vector R1, 2. This is the vector from object 1 to object 2. We know that the unit vector is equal to the vector divided by its magnitude, and the magnitude of that vector is what we're denoting as R12, this distance. And so we can rewrite Coulomb's law in the following form. F12 is K, Q1, Q2, vector R12, divided by, now this looks a little strange, R12 cubed. This is not a 1 over r cubed force. It's still the 1 over r squared force in magnitude because that extra factor of r is embedded in that vector. So these are 2 different ways of abstractly expressing the force on object 2 due to the interaction between these 2 charges. Now, one of the issues, though, in problem solving is we want to get a vector expression in a coordinate system. And so what I'd like to do now is show how we do that. So let's look at this same problem. First, we have Q1 and Q2. So we have 2 charges. And now let's choose a coordinate system. So we're going to put, this is Q1. It's going to place Q1 at our origin. This will be plus x, plus y, I hat, j hat. And what we'd like to do is express this force in terms of our coordinate system. We have these 2 vectors, r1, 2, and r hat 1, 2. Now, if this is the position x2, and over there is y2, our charge 2 has a coordinates x2 and y2. And now what we can easily express both the distance using the Pythagorean theorem and this vector r12. So let's write these out. r12 is simply the decomposition. So we can think of that as the sum of this vector plus that vector. And that's equal to x2 I hat plus y2 j hat. And the magnitude of this vector by the Pythagorean theorem is simply x2 squared plus y2 squared to the 1/2. And now we've expressed all the terms that we need in this expression for Coulomb's law. And so the force on object 2 is the constant K, Q1, Q2. Now here's where this is to the cubed. And what we have is x2 squared plus y2 squared to the 3/2 power. And that's because this is to the 1/2 cubed. And now we have the vector x2 I hat plus y2 j hat. And so we've now expressed the force on an object 2 in terms of our Cartesian coordinates.
We're going to start by talking about a property of matter called charge. And that's even how we'll define it. It's just a property of matter. Now, you've probably heard of charge a few ways, and the way you've heard of it that's probably most relevant to what we're doing is when you charge this, right? You charge your cell phone. And you're charging, of course, the battery in your cell phone because it stores energy. And when you plug it in and you charge it, what do you look for? You look for the little lightning bolt. Right? The lightning bolt tells you it's charging. So in fact, that is all relevant to what we're talking about. The charge, when you charge your cell phone, you are putting in the kind of charge we're talking about here. You're not actually adding charge to it, you're actually raising the charge to a higher energy state. And then when it flows out, you use that energy to do something else, like light up your cell phone screen. And even the lightning bolt, there's a reason it's a lightning bolt. That's relevant. We'll be looking at that as well. So, oh, I got an email. Sorry, no, just kidding. So you charge your cell phone. That's what we're talking about here. Let's look at the where charge comes from. So it's actually not just a property of matter. It is a fundamental property of matter, like mass. This is not just something that kind of depends on what kind of matter it is. All matter can have charge. So we're going to look at then at the deepest level, we're going to draw one of these. All right, here's some circles with ends in them. And then here's some circles with P's in them. And then flying around are some E's. So you know that this is an atom. So we're going to think about where is the charge inside this atom. Well, there's three kinds of particles that make up an atom. There's protons and neutrons in the nucleus. So we have a proton here, we have a neutron, and there are electrons that fly around the nucleus. The smaller, lighter electrons fly around the outside. And bonus points if you can quickly say which element I just drew. Correct, lithium, very good. Now, let's look at the charge of each of these microscopic particles here. So the proton has a charge of +1 e. The unit is E. So E is a unit of charge. It means elementary charge unit. And you can see it's a very convenient unit when you're dealing with subatomic particles because it's 1. It's really defined as the charge on a proton. So elementary charge unit. The neutron has no charge. It's neutral, as the name might imply. So it has 0 E. And while the proton is +1 e, the electron is negative. It is -1 e. So charge can be positive or negative. That's all. So we also, though, want to think in terms of the macroscopic unit. We don't always use microscopic, because if you think about it, if every proton has 1 e, there's a lot of protons in an atom, and then there's a lot of atoms in an object. So the number of the charge could get really big, big numbers. So we also have a macroscopic. So if this is micro, we also have C, which is for Couloumb. And that's the macro. And you can see the connection is pretty big. So 1e equals 1.6 times 10 to the minus 19 coulombs. That's a big gap between atomic and macro scale. 0e, of course, is 0 coulombs. 0 is just 0. And then minus 1e is minus 1.6 times 10 to the minus 19 coulombs. This is, of course, plus. Okay. So you could then use this to convert between the two. You can figure out how many coulombs of charge are on a single proton, very small, maybe on 5 protons, still very small. Or you could figure out how many e's of charge are on some macroscopic thing. You can use either one with that conversion factor. You can also think about we've talked about the charge of the fundamental particles that make up the atom. What's the charge of just the atom? We aren't going to break everything we do into fundamental particles. We also have to think about bigger things. So let's go just a little bit bigger and say the atom. Well, then I would say the total charge on an atom or anything is just the sum. You just add up all the charge. So the total charge here is plus 1, plus 1, plus 1. That's plus 3, minus 1, minus 1, minus 1. That's minus 3. It's 0. Right? This is a neutral atom because the charges balance and they make 0. Okay? So that's the basics of charge and where it comes from fundamentally, and now we'll start scaling up and looking at larger things. We're going to begin with something that is the source of everything we're going to talk about in the entire class, and that is charge. I like to give simple, plain-spoken definitions of things. So charge, we'll say, is a property of matter that creates force. A property of matter that creates force. Even the initial concept of charge can get confusing because we have to jump between charge at the microscopic scale, the scale of atoms and molecules, to charge at the macroscopic scale, the charge of you and me and chalk. Okay? So since that gets confusing, I like to start by describing it in both worlds. 3 protons, it must be lithium. Lithium, very cool element. It was used, it makes grease, and it makes you feel better, and it makes nuclear weapons, and Nirvana wrote a song about it. So there's the 4 things I know about lithium. That's all I got. So now let's look inside this lithium atom and see where the charge resides. Well, it's in these subatomic particles. So we can look at the proton and ask ourselves, what is its charge? Charge of a proton is plus 1e, where E is the unit. E means elementary charge unit. It's defined as the charge of a proton. So this is 1.00, as many zeros as you want. The charge of a proton is exactly 1e. One thing to stress is that E does not mean electron. Sometimes people see that E and they think, oh, that must be a negative charge. The unit must be negative. It must mean electron. It doesn't mean electron. Often we draw little e's to mean electrons. Sometimes we write an E and we mean this particle an electron. Sometimes we put a negative sign on it to clarify that it's an electron. But when you see it next to a number, you have to use your context and realize that doesn't mean electron. That means elementary charge unit. And it is not negative. It is also not positive. It's just a unit. Units don't have signs. The sign comes from the number in front of it. Okay? So if you see a number in front of an E, if it's a plus, then you know it's positive. If you see nothing, we assume nothing means a positive number, so that's also plus 1e. But if it's negative, we'll put a negative in front of it. Okay? But E is not negative. E is elementary charge unit. We can think about the difference between the microscopic and the macroscopic scales by also giving you the charges in terms of the macroscopic unit of charge, which is the Coulomb. So the charge of a proton in coulombs is 1.6 times 10 to the minus 19 C for Coulomb. The charge of the neutron is 0 C. Regardless of the unit, it is 0. And the charge of the electron is the same, it's just negative, minus 1.6 times 10 to the minus 19 coulombs. So a big jump between the microscopic and the macroscopic worlds. We can also, while we're thinking about it, look at the mass. We can also see the jump, or the difference, in the mass. Mass also has a microscopic unit, U. So the proton's mass is 1.007 U, where U is the unified atomic mass unit. If we want, we can think about the macroscopic scale, and we can write these numbers in terms of kilograms. And let's do it. So the proton mass is then 1.67 times 10 to the minus 27 kilograms. So an even bigger difference than in the charge, 27 orders of magnitude in the mass, kilograms. And I'm writing the same number because here I kept up with it to 4 places, and here only 3. So pretty much if you're keeping up to things with sort of 1%, and our homework is only within plus or minus 5%, then these are essentially the same, right? This is a very small difference. And if you are really keeping up with things only to about this level, the electron mass comes out very small, 0.0009 times 10 to the minus 27 kilograms. So again, if you're just keeping up with it to sort of this level, you can pretend the electrons weigh nothing. Right? If you're just estimating based on the mass of something how many electrons and protons and neutrons it has, you can pretty much ignore the electrons. They don't weigh very much. And they're similar in number to the other particles. Okay? So now let's think about how these things get charged up. And now we will do macro charge. Macro just meaning large. So in physics, we often talk about a body. So we don't really mean anything specific by body. Body just means a large object made out of matter. That's pretty much all it means. So what's the first thing we want to do? Well, I guess if we want to think about charge in this rod, we simply say how much charge does it have? And you can actually figure that out from what you already know from the micro scale of charge. Because you could say, okay, this thing weighs 0.37 kilograms, and we learned that the mass of charge was very small, 1.7 times 10 to the minus 27 kilograms per nucleon, where a nucleon is either a proton or a neutron. Just if you're talking about one or the other, you call it a nucleon, things that live in the nucleus. So we have our big mass divided by the mass of an individual nucleon, and you put those together, and you get 2.2 times 10 to the 26 nucleons. So you actually don't need to know the chemistry of this thing, or even what atoms are in it. If we know that it weighs 0.37 kilograms, we know that that mass is almost all in the protons and neutrons. The electrons don't weigh much. Then we can actually estimate the number of nucleons in this thing. Now, another thing we need to know about atoms is that there's usually roughly equal numbers of protons and neutrons in the nucleus. It's almost never exactly equal, but it's usually very close. With lithium, it was 3 and 4, and it's usually closer than that. So if that's true, then we know that roughly half of the nucleons are protons. So we know we have 1.1 times 10 to the 26 protons. Okay? And if that's true, now we can figure out the charge, because each one has a charge of 1.6 times 10 to the minus 19 coulombs per proton. Okay? So if you multiply those two, you end up with 18 times 10 to the 6 coulombs. That's 18 million coulombs. There are 18 million coulombs of positive charge in this macroscopic Teflon rod. Now, if I were really holding 18 millions of coulombs of charge, it would be the greatest demonstration you've ever seen in your life. It would blow you away. I mean, it would literally blow us all away. Out of the room, building would be gone. Okay? But we survived this demo. We aren't all, well, I guess only I and the cameraman would be blown away because this is a distance thing. But we survive because there's not just 18 million coulombs of positive charge. There's also 18 million coulombs of negative charge. This is the difference between microscopic and macroscopic. So in addition to all the protons, there's electrons, and they're so mixed together, so tightly, that we don't see the charge in the macroscopic world. So it does have 18 million coulombs of protons, and it does have 18 million coulombs of electrons. But when you put them together, you get something that macroscopically just appears neutral. And this is how you have to keep in mind about macroscopic objects. When we say they're neutral, they're actually still fairly exciting. There's still a lot of charge in there. It's just completely mixed together and balanced. So we decided my Teflon rod has 18 million coulombs of charge, but it has both positive and negative charge, and they cover each other up, and it comes out neutral. So now we have to figure out, how do you get a macroscopic object to charge up? And the answer is you charge by rubbing. It doesn't sound very technical, but that's actually how electrostatics got started, is charging things up by rubbing. Sort of a crackling sound. Let me hold it close to my mic. It kind of crackles. Right? So you got a sound, and I'm going to bring the charge rod near his arm. And what does that feel like?
It feels really tingly.
Tingly. Excellent. Exactly what it's supposed to feel like. Tingly, thanks. That feeling is called formication. That's F-O-R-M-I-C-A-T-I-O-N. That's a medical term for a tingling sensation. So you always feel that near a charged object. So there we go. We got sound, we have formication. A third effect that you can see with a charged object is I'll take these pith balls. These are little really light balls that have been colored to look nice, and they tend to get charged up. And if I bring the Teflon rod charged near the pith balls, you can see as I move it across, they start to move and they fly around under the influence of the charged rod. So there you have something begin to move. It felt a force. It has mass. It went from 0 velocity to some higher velocity, so we applied a force. So that's 3 things going on. So clearly something is happening with this rod when I rub it with a fur. So let's look and see if we can figure out what's going on. So electrons get loose, and what happens is you end up with more electrons tend to go to the Teflon, and more electrons tend to leave the fur. So what I can do is redraw this row. The nuclei are still there, but now it's sort of deficient in electrons, like that. So if we transfer some charge, now the balance is not neutral. Now the Teflon comes out negative, and the fur comes out positive. That's what's going on at a microscopic scale. This is called the triboelectric effect. And unfortunately, it's very complicated. You can't just calculate how much charge is going to transfer in a triboelectric experiment. It depends on the exact surface chemistry, the previous surface treatment, and the previous surface chemistry. It depends on the humidity in the air, what kind of gas is in the air, how hard you rub, how fast you rub, what kind of fur it is. It depends on a lot of things. It's not really an exact science. An important aspect of these electrical forces is that electric forces obey superposition. That is a big fancy thing that physicists say. They obey superposition. Let me put that in Google Translate for you here. This will help. Let's see. Let's put that in English. Let's see, electric forces add up. That's really all we mean. They add. If you have force due to one charge, a force due to another charge, you just add them. They add, okay, a little bit more complicated. They add as vectors, you could say. That's implied here, because the force has to be a vector, therefore it must obey superposition as a vector. So let's do a quick little problem or look at a situation, and close enough, right? So A to B is D, B to C is 2D. So if these obey superposition, we can use sort of a notation like this. We can say the force, the total force on C is the force that A applies to C. So we can call that FA. I'll do A with an arrow to C. That means the force that A applies to C plus the force that B applies to C. Like that. 2D plus another D, we need that separation. So 3D squared. And that is to the right, because they're both plus Q. We're assuming these are all positive charges, so that pushes to the right. And this one, since they're all positive, will also push to the right. So we don't have to deal with the vector aspect right now. This one would be KE times what? 2Q times Q over, in this case, 2D squared, because the separation is just 2D over 2D squared. And you could simplify that if you want. I mean, they're all going to be KE Q squared over D squared. And what would you get? This would be 2 plus 1 is 3, And this would be, oh, you'd have a different denominator, it'd be a mess. But you could simplify that or plug in numbers or whatever you want. And if you want to give it as a vector, you would know it's going to go this way because both components were to the right. We'll look at it with vectors next. So we've added up some forces on charges in 1D, but we can also add them in 2D. So forces on charges in 2D, and by 2D I just mean they're spread around on a plane, they're not just on a line. In 2D also add as vectors, or I might be willing to say they superpose, they obey superposition. So let's look here. Say we have a two-dimensional coordinate system like this, like that, and we've got a charge up here, QA, and let's go ahead and start giving it some signs. Let's say it's positive, and we've got one at the origin, QC, and that one I wanted to make positive also, and then over here on this axis we got QB, which is negative. We'll make one of them negative. So really you have to work with vectors to do these problems quantitatively. So now we're just going to sort of do them graphically. We'll just look at them and think about, for example, which way would the force on C be? Which way would it be? Well, let's see. What we could do is say the charge magnitudes, why don't we say, are all about the same. And the separations are about the same. So we can kind of do this graphically by saying, well, this is positive and this is positive, so they're going to repel. It's going to be a force kind of like that. That would be force FA to C, right? The one that A applies to C. And then here, positive and negative, it's going to be attractive. So it's going to feel a force this way. It's going to be about the same size, right? It's about the same charges, about the same separation. So I can draw it kind of like that. That would be the force that B applies to C. So if you wanted the net force, you would just have to do a vector addition of these two forces, and it would look something like, well, it's a little bit down. It would be something like that. That's the total force on C. You could actually do it for all three, right? So here, this force is also attractive, and this one would be repulsive, so it would feel a force kind of down. And this one what? It would have a force going up this way. It's repulsive by that one, and it would be attractive like this one. And this one would have a net force kind of that way, right? F on A, force on A. So you want to be good at interpreting diagrams like this and predicting which way a force is going to go, just sort of graphically. We aren't going to get into the detailed vector sum formulas for these. Just a thought experiment. All I have to do is use my fingers and erase the chalk. So in the presence of the charged insulator, I'm going to cut this in half, like that. These didn't go anywhere, right? The electrons are still repelled by these electrons, which leaves this side positive. That's all the same. All we did was cut it with this thing still here. And it was polarized, now it's cut. Now we actually have two charged conductors. Okay? Even if we take this away, these will start to move around and redistribute, but now you have two charged conductors. Ooh. So this is a way to charge something up other than rubbing it with fur, right? This is called charging by induction. So let's look at doing this in the real world. So I have two aluminum spheres here. So these are going to act as the neutral conductor. And I have two, that way to cut them, all I have to do is separate them. Even though they're just barely touching, that's good enough to let free electrons flow from one to the other. What I'm going to do is have my charged rod here, and I'm going to bring the charged rod up to one of them, and it's creating the polarization effect. It's polarizing the two spheres, and then I'm simply going to separate them in the presence of the rod. What that should do, it should have, let's see, the free electrons were pushed this way. This one should be negative, this one should be positive.
Goes all the way back. Chapter 23 starts with something you've definitely learned before, which is the law of charges. The law of charges, you probably learned it maybe in 6th grade, at some point in middle school. Who can tell me what the law of charges is? Travis.
Like charges repel.
So like charges attract, like charges repel, unlike charges attract. Like charges repel, unlike charges attract. So we have the different names of the different charges. What are the names, Dorfstetter, of the charges? Say again? Oh, well, those would be the particles. I agree. We have an electron and a proton, but even more basic, the charges are called. Vlad? Positive and negative. We could have called them green and blue. We could have called them guacamole and all of those. Okay? But realize that they were just picked as positive and negative. In fact, there's nothing about one charge that you would call inherently positive or inherently negative. I don't really even know what those really mean. It's just that we have positive and negative charges. Mathematically, of course, this makes the most sense. All right, we can cause charge by, we can cause a charge via various different ways. One is conduction. Bless you. All right, charge via conduction. For example, I could take the rubber rod and I can put it against the dead rabbit. And when I do this, we get negative charges from the dead rabbit, which go onto the rubber rod. So the rubber rod now has negative charges. But this isn't very exciting. So let's try a different example. We'll do this one. If I take the balloon and I rub it on the dead rabbit, the balloon is again made of rubber. So we have negative charges going from the dead rabbit skin to the balloon. Then I can take it, I can do this. And it sticks to my head. So, same is true actually if I do it, rub it on my hair, okay? So, when I do this, we get negative charges from my hair going to the balloon, and the balloon is negatively charged. So why then does the balloon stick to my hair? Tyler?
Because your hair is positively charged.
My hair now has a net positive charge, and the balloon has a net negative charge, so they attract one another. Okay, good. If I do this correctly, when I take the balloon away, my hair, part of my hair should be sticking up. Yes? Okay, why is part of my hair sticking up? Emily?
Because it still has a charge. Because the brown one.
But why is my hair, like I understand like these two stick together, but the question is, why is my hair now sticking up like this? John?
It's positively charged, so it repels each other.
So my hair, which is positively charged, is repelling itself. Okay, so then we can also do this, which we'll talk about in a little bit. Okay, that's charge via conduction. When the two objects actually touch one another, a charge flows from one object to another. That's charge via conduction. We also have charge via something called induction. Now, charge via induction is we're going to induce a charge. Now, this is what I consider to be one of my worst demos. It's one of the hardest to see, but regardless, I will do it for you. Here we go. We have an electroscope. Oh no. Whew. Good morning. Right here I have an electroscope. An electroscope is an instrument for demonstrating electric charge.
Flippin Physics.
This electroscope has a metal ball on top of a vertical metal rod with a hook on the end of it and two thin foils of aluminum hanging from the hook. That whole apparatus is electrically insulated from its surroundings via the rubber stopper and glass flask. Let's start by charging the electroscope via conduction. First, I will do the entire demonstration, then we will go through it step by step to make sure you understand what is going on. So class, are we ready to demonstrate charging via conduction?
Absolutely.
Yeah. Sure. Here we go. First, I'm going to charge this rubber balloon by rubbing it against fur. So now we have a charged rubber balloon. I bring it close to the electroscope, and you can see the foils of the electroscope begin moving apart. And then when I touch the electroscope, I have now charged the electroscope via conduction. So this is a charged electroscope via conduction, and I can touch the electroscope with my finger, bink, and the two foils move back to where they started. That's it. All right, so I apologize to those on the ends. It might be difficult to see if you want to move a little bit, you can. Okay, the electroscope, basically what it is a piece of metal attached to very thin metal foils here, and when the metal foils carry a charge, you can see how the charge is affected. So we have now a net negative charge when I take and I touch the electroscope with the net negative, with the negative charge. There we go. You can see what happens to the foils, because now the electroscope has a net negative charge. So what happened to the foils, Bill?
Both negatively charged.
Okay. So same thing as my hair, they both have the same charge. In this case, they have a negative charge, so the foils actually move apart from one another, going back to the law of charges, because like charges repel. Now, when I take my finger and I touch the electroscope, bing, the foils go back toward one another. Why is that, Tim?
Because the charges went back to your finger.
Went back to my finger. What I did is I grounded the electroscope. Okay? I am attached to the ground. Basically, the ground is a giant well of charge that we can take and give charge to, and it's considered an infinite well of charge that you can give and take charge from as much as you want. So that, again, is still charge via conduction. Now here is the demo. Get excited. Charge via induction. The idea is I'm going to induce a charge in the electroscope without ever touching it with the charged object. Here we go. So I have a net negative charge on the rubber rod. I bring it close to the electroscope, but I do not touch. I then ground the electroscope. I remove the ground and watch carefully. Bing. Oh, I'll do it one more time in case you missed it. Here we go. It's that last moment, so it's really subtle, so you gotta watch carefully. When I remove the rubber rod at the very end, the foils move apart. Here we go. Okay, I bring it close. I ground, I remove the ground, and bing, they move apart. I know. And we will now ground it. Okay, so what I want to do now is actually walk through what happened there with the charges. So I'm actually going to refer to some pictures in your textbook on page 710. I'm going to put them up here, but it's good for you to have the pictures in the textbook as well. So on page 710, you will find we have, of course, today's desktop picture, which is a picture of Ryan this fall when we were going through and raking leaves. All right. Okay. So this is, they've illustrated the electroscope via a giant sphere. I don't know why. But the electroscope, to begin with, has a net neutral charge. Now, it's important to realize that when we say the net charge on the electroscope is 0, we're not saying there aren't any protons or electrons there, right? There are a whole bunch of protons and electrons. It just happens that they have an even number. So we have the same number, the net charge is equal to 0. This is what it looks like before I bring the rod close to it. This is when I bring the rod. Now, I bring the rod next to the electroscope. The rod is negatively charged. So the negative charges are then pushed away from. Notice the positive charges are the protons. They're in the nucleus, so they don't really move around. It's the negative charges that move around. So the negative charges are repelled from the negatively charged rod, and they're then repelled down into the foils. And so when I brought this close, the foils actually moved apart. Then I grounded it. This, just so you know, is the international symbol for a ground, and you do need to know that symbol, so you have to be able to identify the grounding symbol. So it is then grounded, and what happened when I grounded it? Look.
All the negative charges went back to where they were at the beginning. So then
Actually, if you look, they don't go back to where they were. This is where we started, right?
yeah.
So then here, when I bring it closer, all the negative charges are pushed farther away, and then what happened? It's okay, help them out. What happened to the negative charges?
They like moved through the wire to the ground.
They moved through the wire to the ground. Now, not all of the negative charges, clearly, but some of the negative charges moved through the wire into the ground. Then I remove the ground, and then I remove the rubber rod, and what we end up with is a net positive charge on the electroscope. Okay? So going all the way back to the beginning, we started out with a neutral, bring in the rubber rod, it causes the negative charges to move away from the negatively charged rod, then some of them move down the ground, and when I remove the ground and remove the rod, we end up with a net positive charge on the electroscope. This is an induced electric charge. It is induced because it was never actually touched by the charged rod. That's what it means to induce a charge.
And if the charge is more, it will go out even further. I don't have an electroscope now here, but what I want you to see that if I charge myself up and I hold in my hand these Christmas tree tinsels, that in a way, if I get enough charge on me, then these tinsels will spread out. It's an idea that immediately follows from the fact that you get a certain amount of charge, whether it's negative charge for me or whether I'm positively charged, that doesn't make any difference. These tinsels will spread out. And of course, the best way I can do that is by charge myself with the Van de Graaff. And as I said earlier, experiments of this nature are not entirely without risk. And so there's always the possibility, of course, that I don't survive this demonstration. But don't worry, because in that case there will be someone else who will lecture 802, except he is not likely to show this demonstration again. So you might as well take a close look, because this may be the only time you will ever see it. So I will give you some nice light on the Van de Graaff. And it's always a scary moment for me. Sleepless nights about the Van de Graaff. Am I going to turn it on, Marcos, or you have the courage to turn it on? You will turn it on? Okay, hold it, Marcos. This is too close for comfort. You ready? Are you nervous? See you. So look at the tinsels. And try not to look at me, please. Go ahead. I am now a living electroscope. If the weather is cooperating today, and if I had long hair, you might even see that my hair would start to act like an electroscope. We can try that too. Why don't you throw it? Is it working? Okay, well, this weekend make sure you take this nylon shirt off in front of the mirror and enjoy your enjoy the experiments at home. Don't try this ever. See you Friday.
Storm chasers risk their lives for a glimpse inside one of nature's most fascinating marvels. Through scientific study, many attempt to predict where and when these devastating events will occur, but forecasting is still a challenge. Thunderstorms are very turbulent environments. Strong updrafts and downdrafts regularly occur, causing water droplets to collide with ice particles. Electrons are sheared off of ascending particles and collect onto descending particles. This separation of charge causes the top of the cloud to become positively charged and the bottom to become negatively charged. As a result, an electric field is established that continues to strengthen as more and more charges are separated. Once enough charge has accumulated, the electric field overrides the atmosphere's insulating properties, resulting in lightning. This event happens about 40 times every second worldwide. These forces of nature can produce amazing light shows, but are best viewed from a safe distance.